This is a video lecture for Math 283. The topic today is projectile motion. We're actually going to cover a second topic in class, which has to do with the tangential and normal acceleration, but I'm not going to talk about this in the video lecture. I'm actually just going to give you guys a theoretical overview of projectile motion, and then we'll do an example problem with projectile motion in class, as well as talk about acceleration. Everything in projectile motion is based off of Newton's second law, which I gave to you guys in the previous class, and it's F equals ma. This should be familiar to you physics folks out there. This is Newton's second law. It's a fundamental law of motion, and we can use this to find the acceleration. So specifically with projectile motion, what's the idea behind projectile motion? The idea is we take some object and typically we'll fire it at a certain angle. This object will go up and come back down. So we can imagine we have some kind of launch angle alpha. We fire it with an initial velocity v0. Okay, so either we throw something or we fire it out of a cannon or a gun or whatever. We send it out at a launch angle alpha, an initial velocity v0, and then this projectile will travel through the air and it will follow a parabolic path, and eventually it'll come back down and hit the ground. And the assumption here is we're assuming the only force acting is gravity. That's the assumption. Now, is that accurate? Well, there's another force acting, that's air resistance. We're going to ignore air resistance in this case. And air resistance has small effects on the trajectory of the projectile, but we're just going to ignore it to make our lives simpler. It gets a lot more complicated when we include it. So we're assuming the only force acting is gravity. And at any point along this projectile's path, we could write this force as Fg. Okay, and Fg equals mg. Okay, where that's the mass of the object times g, which is the gravitational acceleration. And that is 9.8 meters per second squared. But because the gravitational force acts downwards, we're going to put a negative in front of that in terms of our acceleration. So the acceleration of this projectile during the entire path is minus 9.8 meters per second squared. Okay, in the j hat direction, or minus j hat direction. So for the whole path, the acceleration is the same. That seems a little bit counterintuitive, but that's true. And this is a constant acceleration downward. So as the projectile goes up, gravity's constantly trying to force it down, and eventually it wins, and it goes back down to the ground. Okay, we want to find equations for the velocity and acceleration, velocity and position, given our acceleration. Now we know how to do that because we did it in the last class. The velocity as a function of time is equal to the integral of the acceleration times dt. Okay. So now we're going to integrate. I think I'm going to leave this as g. I'm going to leave this as g. This is equal to minus g times j hat. So I get the integral of minus g dt j hat. Okay. And if I integrate this, I get minus gt plus an integration constant c1. This is j hat. Minus gt j hat times an integration constant c1. Now how do we find c1? We use the initial conditions. The initial conditions say that the velocity at t equals 0 is simply equal to our initial launch velocity, v0. And this is equal to c1. So this means that we can write the velocity as a function of time as minus gt j hat plus v0. That's our initial velocity. Now let me mention right here, the initial velocity can be written as having two components. So we have a component v0 cosine of alpha, okay, times I hat, plus v0 sine of alpha times j hat. This is our initial velocity. And here v0 is simply the initial speed. So v0 equals the magnitude of our initial velocity. Okay. Or in other words, it's our launch speed. And so we can write v of t as being equal to, if we combine all of this together, right, we can write v of t as being equal to v0 cosine of alpha times I hat plus v0 sine of alpha minus gt times j hat. So this is an equation that gives the velocity as a function of time. Okay, let's also find the position as a function of time. So we know that r of t is equal to the integral of v of t dt. So we're going to take an integral of this function here, and if we integrate this function, we get the integral of, actually, do I want to integrate this? Let's see, yeah, I'll integrate this entire thing here. So we're going to get, I was debating whether to integrate this or this, but I'll integrate the more complete expression down here. So we're going to integrate this, and actually I'll skip the integral step, or I'll just go ahead and integrate this. We're going to integrate this whole thing. So if we integrate, we get v0 cosine of alpha times t, right? This is a constant, times t I hat. If we integrate this, we get plus v0 sine alpha t, right? v0 sine alpha t minus, and now if we integrate t, we get t squared over 2. So we get 1/2 gt squared, all of this, times j hat, okay? Plus, we get a second integration constant, we get c2, okay? Now, let's figure out what c2 is. We can use our initial condition. So the position of the projectile at t equals 0 is at the origin, and so that's equal to 0. And if we plug in t here, all these terms go away, so we get 0 is equal to c2. So the second integration constant, as long as we start at the origin, as long as we start at a height of 0, this second integration constant is 0. Now we'll do a problem in class where we actually fire this object from a cliff. In that case, we're not starting at, our initial position is not 0, so we'll talk about how to deal with that in class. So basically this is, we can erase the c2 right now. And this is our equation for r of t. Now if we write it in terms of x and y, x of t equals v0 cosine of alpha times t, and y of t equals v0 sine of alpha times t minus 1/2 gt squared. Okay, that's the y component. So these are parametric equations. These are parametric equations that give the position of a projectile as a function of time as it goes along this path. Okay, and what's interesting here, by the way, is if you were to watch the x position depends on t linearly. And so as this projectile moves along, the x component just moves at a constant speed or velocity. So if the sun were directly overhead and you were watching the shadow of this projectile, you would just see the shadow move along at a constant speed. That's an interesting aspect of projectile motion. Okay, final thing here is I want to find an equation for what's called the range. And the range is basically this distance. The range is the distance the projectile travels. Can we find an equation for that range? Okay. Well, when the projectile hits the ground here on impact, we know that y will equal 0, okay, on impact. And so we're going to use that fact. We're going to plug in y, 0 for y. So 0, this is only when it hits the ground, by the way. So 0 equals v0 sine of alpha t minus 1/2 gt squared. Okay. And what we can do is factor out a t here. So this leaves us with t times v0 sine of alpha minus 1/2 gt. Okay, and all this equals 0. So either, what this means is either t equals 0, or this whole thing equals 0, or v0 sine of alpha minus 1/2 gt squared equals 0. Now if we solve for t here, in this case, what do we get? We get t equals, oh excuse me, this is t, not t squared. So t is going to equal 2 v0 sine of alpha over g, okay? Now this t equals 0 corresponds to the time when the projectile is launched. And this t equals 2 v0 sine alpha over g corresponds to the time when the projectile hits the ground. So we now find the time of impact, and now what I'm going to do is plug this time into my equation for x to get the range. So the range is going to be equal to x of t, where I plug in this specific t, the t of impact. So I'm going to plug that in here, and I get v0 cosine of alpha times 2v0 sine of alpha g. Okay, then we can simplify this, and this equals 2v0 squared sine of alpha cosine alpha over g. And if you guys remember that trig identity, 2 sine of alpha cosine of alpha equals sine of 2 alpha. We're going to use this trig identity. So we can write the range as range equals v0 squared times sine of 2 alpha divided by g. So let me box that equation. This is the equation for the range of a projectile fired with an initial speed v0 and launch angle alpha. This is how far the projectile will travel. And one thing to note here, by the way, this function is maximized when alpha equals 45 degrees, okay, because that means you get sine of 90, which is a maximum value of sine. And so what that means is, in the absence of air resistance, if you want your projectile to go the farthest, you should launch it at a 45-degree angle. In other words, theoretically, for a given initial launch speed, if you're like a baseball player and you're at home plate, you're batting, you know, if you want the ball to go the farthest, you should try to hit it at a 45-degree angle, ignoring air resistance. Okay, in class we will do an example problem. We'll do a specific example problem for projectile motion where we fire an object from a cliff, and then we'll talk about the normal and tangential components of acceleration.